This is Howie. He just graduated from University of Southern California. Also, he'll be co-instructing. I'm going to take the first half of the lecture. He's going to take the second, and we're going to talk about theory of quantum channels for photonic quantum networks. Let me just say real quick, by the way, Howie, when it's on this first half, just if you see anything in the Q&A pop up that you can answer yourself, like typing, then just answer it. Or if it needs me, then I can address it. Just point it out to me if you don't mind. Okay, so let me make so I can see better. Make this thing smaller and turn my phone to silent. There we go. Okay, great. So yeah, let's get started. So we're going to write the theory of quantum channels for photonic quantum networks, and let's see what this means. So next slide, Howie. So here's the layout. So I've been doing this course as a co-instructor the past like maybe 2 or 3 years, and this is the general layout. Haven't changed too much, but I just want to say that it's kind of most of it's more formal and mathematically formal than physical and giving you a bunch of numbers and things like that. And so a lot of it's just about quantum channels and quantum information and how to deal with that at a mathematical level, but try to sprinkle some physical things throughout. Okay, just some like so for example, in quantum channels, I'll give you like physical examples of quantum channels and how they arise. And as always, this isn't a talk, it's not a seminar, it's a lecture. So please, if you need one of us to slow down or stop or explain something better, or if you're just generally confused, then type something in the Q&A and hopefully we'll see that and resolve. All right, great. So next slide, Howie. So yeah, let's just get started. Okay, so we're currently in this era of like quantum engineering and quantum control. At the beginning of the 1900s, this is sort of the birth or the dawn of the quantum with 1905 and photons and 1925 and Schrodinger, and you can push it into QED and things like that. But right now we're in the era of engineering that stuff that people started discovering in the early 1900s. And so now we're leveraging quantum, not only trying to understand them, but leverage quantum concepts to gain some benefit to society, hopefully, as a whole, but maybe just a handful of scientists, right? So there are several things that we do with quantum systems now. We engineer quantum systems to make really good sensors. Okay, so this is something I theoretically work with a lot is quantum sensing and how as well. And so there we use like maybe many body quantum states or use some non-classical sources such as fancy light, like squeeze light, which is used at LIGO, to have improved sensing. So LIGO, measures gravitational waves, and they use squeeze light to get better precision on their estimation. And they can even that even allows them to reach like a higher volume of the sky, right? So a larger volume of the sky. That's one modality, quantum sensing. Another one is quantum communication. So now it's just typical communication where we want to talk to each other, but now we do so in some quantum fashion. So this is like people do secure communication. This is quantum key distribution and things like quantum teleportations, fancy things. And people do this on the ground through fiber, as well as with with satellites. So for example, there's this Mischief satellite or MOTSI Chinese quantum science satellite that distributes entanglement from the ground to the sky and does cool experiments. I actually have a model, a little toy model of it in my on one of my bookshelves. So that's something people do. Yeah, that's a fun fact, Hoey. There you go. Got that from John Dowling. Okay, so the another thing that's probably the most popular, modality is quantum computing. All right, so now we're doing computing, but with quantum states. And I don't know, I mean, there's a lot of money into quantum computing. There's a lot of hype into quantum computing because of what it might promise. We're not completely sure about what it can do, but we're all excited about it. And so that's the quantum part. And next slide, please, Howie. Oh, and another thing, which is nice, and this kind of puts all these things together on a large scale, is quantum networking. All right, so maybe you have small quantum processors, small quantum computers, and they're distributed across a network, like in this picture below. It could also be quantum sensors distributed across the network. All right, and you want to do some sort of large scale processing or distributed processing, or also some distributed sensing where maybe you're measuring values of a field at this location and far away at this location, and you want to get the best sensitivity you can. And so this describes a quantum networks. At the smallest level, it's just a distributed set of quantum information processors that are possibly linked by entanglement and sharing quantum information. All right. And so studying quantum networks, you're trying to study how best to link these things, which is much different than a classical network because quantum states and quantum information is fragile. Right. Okay. Is there a way to, by the way, Howie, is there a way to, you have to scroll a bit. Is there a way to like
Yeah. Um,
fit it to the page a bit
well,
better? So,
I'm thinking, would this be better? But well,
uh, could you go click,
something like this.
let me click view
Um,
and then,
which one?
uh,
Maybe
click view
uh,
and then maybe full screen mode.
view screen. Oh, this. Thanks for mentioning. Yeah, this one.
Yeah, that's perfect. All right. Yeah, that's great. Um, so yeah, that's through quantum networks, people have to how to link all these quantum information processors over large scales. And the reason that's a bit challenging is because these links are generally noisy and states are often fragile. Um, Someone asked a question, will you share the slides at the end of this session? We can. Certainly can. I guess is that a plan, Brianna? Do we usually share slides? Certainly can. I don't mind it. Um, yeah, we'll see. Okay, so yeah, next slide. Um, so I said the quantum systems are quite generally, um, but when I say quantum information processor in the abstract or quantum sensor in the abstract, but physically this could come in many different forms. All right, so many different systems. Here's just one handful of them. There's like about four handfuls of them, and people work on individually on all of these. And if you're a real good theorist, maybe you know a good bit of these yourself. And so, for example, NV centers, this top left, people, especially in CQN, are really interested in working with these NV centers because they make a really good long coherence time qubit. Um, and that's good for like networking purposes. People work on superconducting transmon qubit. This is Google Sycamore. I think we're past Sycamore now. We're at Willow or something. And people use these things for trying to build quantum computers, but also you can leverage transmon qubits as sensors. So that's nice. Similar thing with trapped ions, and then there's all these other platforms as well. For example, like bulk optics, like maybe you can think of just a optical table, or nanophotonics, where now you shrink the optical table down to very small sizes and you stitch them on some board. Okay. Um, so that's that. Next slide, Howie. And where does optics come into all of this? I said in the beginning, this is the theory of quantum channels for photonics or optics. For photons, where does optics come into all this? Where do the photons come in? This is straightforward where it would come in a quantum networking thing, right? So if you have large distributed quantum processors, the immediate question is how do you link them physically? You're likely not going to send electron beams or transport physical ion from one across several kilometers. The best way to do, of course, to do that would just be to send photons, natural flyers. Uh, yeah, natural flyers. Someone just real quickly, someone said trapped ions question mark. Um, I'm guessing what you mean by when you say trapped ions question mark, if you're just asking generally what that is, just like a positively charged, ion, and it's trapped in some electromagnetic potential. Maybe it has some spin degrees of freedom that you can treat as qubits. It also has motional degrees of freedom because it's trapped in some harmonic trap. And then you can play with both of those to act as sensors or qubits for information processing. Okay. So back to this. Yeah. So quantum networking, how do you link these nodes in this network? The best option is by optics, by sending stuff over fibers to maybe even couple in V centers like this top right figure, or even over large scale, like satellite isn't beaming electron beams, they're sending photons to distribute entanglement. But there's also even at the computing scale, even at sort of quote unquote small scale things, people are trying to build photonic quantum computers, not just ones with transmon qubits or trapped ions, trying to build photonic quantum computers. So this is like a linear optical circuit to play with the states of light. Okay, next question. I mean, next slide. Sorry. Okay, so pause. First poll question, zeroth order poll question for everyone. So I'll just read it and okay, Howie has opened it already. So we'll just read it. I'll just read it out loud. And so let's see. Photonic quantum information processing. What are photons good for? Zeroth order. I think everyone should hopefully get this. I gave some examples of a photonic quantum computer. Of course, if we want to do quantum communication, we got to do it over a large scale. What are we going to use? It's a good question. I didn't say anything about photonic quantum sensing, but maybe you can think about that for a second. So let this run for about 60 or 90 seconds or so, and then we'll close it out once like about 90% of people have answered. So we'll give you guys like 20 more seconds.
5 seconds left.
Give them about like 15 more seconds.
15 more. Okay.
Yeah.
Okay. Time is up.
Okay. In the poll. Can I share? Am I sharing results right now? Are we sharing results? I don't know. So a large portion of people said all of the above. That's true. Um, so I'm trying to exit out of this. Yeah, so photons are good for just about anything. They may not, I didn't mention quantum sensing, but the biggest example of like a quantum sensor would be an interferometer. And this is what LIGO is. LIGO is a big L-shaped interferometer where you can just think of they have light that goes down one arm, light that goes down another. There's these massive mirrors that wobble due to gravitational waves. And there's another massive mirror that wobbles due to gravitational waves. This light travels down here, bounces off the mirror and comes back, and then the gravitational wave gets imprinted on the phase of the light, They interfere the incoming light on some kind of you know, beam splitter type thing, which is just you think of just a piece of glass, and then they detect it, and they ask, well, is the gravitational wave there, and what is its form, and what does it look like in time? Okay, and so yeah, it's good for sensing. Photons are good for sensing. Quantum computing, I don't, well, I mean, we don't really know what's good for quantum computing, but I mean, people are trying to build photonic quantum computers. PsiQuantum is a company that's trying to do that like on chip, and several other people are trying to do it. Maybe not with optical, but also people considering it with microwave, so microwave photons and things like that. So, uh, photonic quantum computing is still in the game. Quantum communication, that's probably the most obvious one because if you're going to communicate, you're going to do it over basically optical fibers or in the air, through the air, which is what we do classically, right? You have optical fibers running to your home to get internet and all kinds of things. So it's good for everything. Okay, next slide, please, Howie.
Yeah.
Yeah, very versatile. Yeah, quantum sensing, microwave cavities, quantum optical setups, and quantum information processing across long distances like communication will require quantum optical interconnects. All righty. All right, next slide, Howie. Okay, so now we're gonna jump into that was all very soft. And so now we're gonna jump into a little bit, well, a lot more formal things. So let's get started. We'll start with a general theory of quantum channels. So just to go over some notation, people pointed this out before. Hopefully everyone at least has some inkling about, or a pretty good inkling about quantum mechanics. We won't go over and we'll go over some basic principles of quantum mechanics, but they're sort of high level. So hopefully everyone at least is familiar with most of these things that are on the slide now. And if not, there should have been some slides, I mean, some notes that were passed around. But I'll just briefly go over these things now. So Hilbert space, that's just some abstract, complex vector space. So it's just a space of little vectors that are possibly complex. So real number times a phase. Think of it that way. It's some large dimensional space and we'll describe the state of a quantum system, the pure state by some ket. This is like a big arrow, and psi, and that's just some ray in this Hilbert space. Okay. Just some other things. Identity operator. We'll show it like that. Unitary operator, which takes states to states, pure states to pure states and gives you coherent quantum evolution. We'll always give it a hat and put a U on it. Quantum channel, which is like a generalization of a unitary dynamics to noisy dynamics. We'll always call these script letters. And then we'll start talking about photons, and photons are tricky little things, but you can always describe them as like a harmonic oscillator. Oops, a quantum harmonic oscillator. And so all this stuff is photon stuff here down. So this is the creation annihilation operators. If you're familiar with those, we'll go over that as we go along. Q and P, again, you can describe photons as, more or less harmonic oscillators. So this is like position and momentum of harmonic oscillators. Call a Hamiltonian H, vacuum state or the ground state. We'll write it like this. And then we'll introduce, because we're dealing with information and encoding information in a photon. Uh, when you talk about information, you talk about bits like 0 and 1. And we'll call these bits, these computational states, and we'll denote them like this. Okay, so that's just a bit of notation. So let's get started on the real stuff. Okay, just some fundamentals. I'll start with the church of the larger Hilbert space. Some of my favorite things about quantum mechanics. So, this is you can sort of take this as like scripture or a tenet of quantum physics. So there's this taken all together, our universe evolves under unitary dynamics. That means if we include everything, such as the system that we're trying to actually probe, or the environment, which may include some reservoir that I've written here, plus everything else, then the global state of all of that is always a pure state. Okay. So on the last slide, I wrote, you saw a pure state and I wrote it as a vector. You can also have a mixed state, which is actually a matrix. It's called density matrix, a mixed state, which we're at like this. But density matrices always just come about, these mixed states always just come about. You can always think of them as I don't have access to everything. I just have access to a small portion of some global system. But I can always, if I have access to everything, I can always describe everything in terms of a pure quantum state psi. Okay, next slide, please. Um, yes, so mixed states come from ignoring the environment. Mathematically, this is described by partial trace over an environmental system. So this is the statement. This is the statement here. So what we're saying is that the joint state of the system and environment, system S, environment E, is always in some pure state SE. And then the system is always, if it's in a mixed state, then it can always be described in this fashion. Okay. Where this is some partial trace. All right. And this is kind of actually defined below. So we can always write any pure state in this form. This is called a Schmidt decomposition of the state. And the trace over the environment is basically just acting, this operation trace E is just acting on the left and right, but only on the environmental states, which is indicated by this I with the subscript E, and then summing over all these environmental states. And then at the end of the day, what we have then is we have this mixed state, rho S, is described in this fashion. This is actually like it's a convex combination of states. You can think of it. I mean, that's exactly what it is. But this is here, lambda J's are the eigenvalues or rho S. Physically, what this is just that if J is some eigenstate, so some basis state in this vector space, then the value lambda J is just the probability to measure the outcome J. So the probability that that when you do a measurement on rho S, then the state is there. Okay, so somebody asked a question, what does the partial trace correspond to in practice? I mean, in practice, like I said, is like a partial trace is like it's like not having access to something. So one physical example of a partial trace is, let's say I have many different photonic modes. If I'm collecting, let's say there's many different distinguishable photonic modes, right? So maybe the top mode is a red frequency, the next mode is a blue frequency, etc. So there's many different photonic modes. And then I have some thing, I'm collecting them, and then maybe what I do is I only measure, or I'm only interested in one of the modes, maybe the top mode. And then what I do is I just throw the other ones out. Okay, I just completely discard them. I don't do anything with them. Maybe my detector or my collection system can't even process them. Or maybe I'm doing it on purpose. I'm filtering. Okay. So then all I do is look at one mode. What I'm doing then is I'm ignoring these modes, which is equivalent to a partial trace. Partial trace on the rest of these modes. So physically it's discarding. So take a whole system and then discard subsystems and only keep one subsystem. So that's physically um, what a partial trace corresponds to. Okay, hopefully that clarified. Okay, next slide, please. invert the process. So this is where this kind of name of church of the larger Hilbert space really comes from, and this is why I like to think about it. Is so, in practice, we don't always start with a global state and a global system and then whatever. We always start with like when we have access to a system, right? We don't have access to everything. We have access to a system, rho s. And so this is the rho s from before. So we can sort of go backwards instead of starting with a global state and going down to system level. We can sort of start from system level and go up to global. And so now what we can do is actually take this mixed state we originally have. We append an environment to it, right? With some basis J of E, which I've written here. We can append an environment to it, and then define some global state in this form. So this is the state from the previous slide. Okay. And so in this way, we can actually start from this mixed state and then take it to a pure state. And if necessary, we can sort of continue this process indefinitely until the entire state of this sort of Uber system is a pure state. And so this is the sort of church of the larger Hilbert space, is that we start with a Hilbert space S, H of S. So this describes the state of the system. So the state of the system lives in this space. But then we go to a larger Hilbert space, SE, which now describes not only the system, but the system and the environment in a joint fashion. So it's actually it's quite big. And this is the sort of church of the larger Hilbert space where all entities are pure and saintly. All right. And so that's what we can always do. And that's just a cool concept to play with your mind a little bit. If you always think about things as being in mixed states, then maybe we can just keep adding things to our system and then always describe everything in terms of pure states. So that you can ask yourself, is the universe in a pure state? And if not, then what do we need to purify the universe? And where does the Hilbert space stop? Okay. Okay, next slide, please. So the next thing, so that was about states. So this is about dynamics, so unitary dynamics. Um, so yeah, quite generically, we can always describe the evolution of a system, of a quantum system, rho s, as an interaction with an environment, and the environment will be in a state as well, sigma E. And we can always describe the interaction process by some global unitary. So this is this global unitary, USE, acting on this initial uncorrelated state, rho s times sigma E. Okay, so there's some initially S and E, or you can think of it this way, initially the system environment are uncorrelated. They're just described individually, but then they interact by this global unitary, and then that gives you this globally correlated state. Next slide, please, Howie. Okay, and this will lead us to finally to the definition of a quantum channel, which is a generalization of a unitary evolution. So, so what is the state of the system by itself after evolution? Okay, so if we take this big picture, like we had before, of a global state. In this case, the global state is just it's just of this form. And then we interact it with the environment, and now we say, okay, we don't have access to the environment, so we're going to trace out these uh, these environmental modes like from before, but I still have access to the system. So what is the state of the system? Okay. Um, and it is what we kind of did before. Okay. So this is the state, the global state after unitary evolution. So what we start with is we start with a state rho SE equals rho S cross sigma E. And I'll say this now, but this sigma E, it can always be taken to be a pure state. It doesn't need to be a mixed state, but we'll just say that it's like this for now. And then the system couples to the environment. So you can imagine physically, maybe you have some photons in a cavity and they're leaking or I mean, they're leaking out of the cavity, but then there's, this cavity's in a hot room, and so it's exchanging energy with the hot room, and so that sigma E is like the photons in the hot room. And this USE is then like some interaction that allows for the leakage and transfer of photons between the walls of the cavity to the hot room. And so then we have rho SE. This is after evolution. USE dagger. And then as before, we say, oh, what's the state of the system? Well, we're going to trace out the environmental modes we don't have access to. So we're simply going to trace them out. And that gives us this guy down here. And generically, you can define a quantum channel precisely this kind of manner. So we have the quantum channel N is some input output map. So we have some input rho of S and some output rho of S prime, and we'll define the quantum channel as this output here. So what we have is that we have again, this generalizes unitary evolution. We have some input rho of S into this quantum channel, which is some linear map N. And any quantum channel N can be described in precisely this manner, where we have a system and environment interacting by unitary, and we simply trace over the environment. Okay. Yeah, in mathematical language, this is a completely positive, trace preserving map, which is a lot of words just to say that the output state in rho of S is a valid quantum state. That's all that means, is that it's a valid quantum state. Like for example, the eigenvalues of n rho of S, they're positive and they correspond to probabilities. Okay. And that's more or less the statement. Okay. But that's what CPT P map means. It's just the output state let me leave that up for a second. The output state is a genuine quantum state. An example of this is output state of a photon. So let's say I inject photons into a fiber, and it's in a pure, nicely formed state because I've made it and I've been real careful with my laser. I've made it with a laser and I've been real careful with my laser. So it's a nice, pure quantum state. But now I'm injecting those photons into a noisy fiber, where the photons can scatter out of the fiber. It can interact with phonons and gain some heat into it or whatever. And so the output state of the photon is no longer this pristine thing that I generated, but now it's some noisy state. And we'll actually give an example of that explicitly later. Okay, next slide, please, Hallway. Nice. Yeah, so if you need a glass of water, get a glass of water, everybody. We're here for 3 hours. Well, by the way, we'll take a 15-minute, about halfway through, we'll take like a 15-minute sort of intercession. Everybody can stretch for a minute, go potty, get yourself some refreshments or whatever. I got 3 kids. I got 3 young children, so I use potty. All right, so anyways, so again, this is how we'll define a quantum channel, is directly from a unitary evolution. And there's another nice way to write a quantum channel, which is extremely useful when you start playing with things by hand in theory, and that's in terms of this Krauss decomposition. And so we'll do the following thing. Okay, so recall that, so we'll define a quantum channel in this way, right? So it's some unitary acting on some joint state, and then we trace over the environment because we don't have access to it. Okay. What we'll further do is we'll take the environment to be in a pure state, and we'll just label it in this manner. So it'll be some pure state E naught. This is just some random labeling. And just to be clear, I said this before, but this is you say, oh, is that special? Can we are we always allowed to do this? And yes, we are always allowed to take the environment in a pure state. It's just always possible to do that if we make the environment large enough. Okay, so yeah. And so now we're going to do this trace. To do the partial trace, you always just pick some basis in the system that you're tracing or the things that you're tracing over. Here's the environment. You just pick some basis. Again, remember this is some Hilbert space, H of E. It's just some vector space as a basis, just like Cartesian coordinates has a basis, and you can rotate those coordinates. So you're free to pick a basis. So we pick up basis E. We do this partial trace explicitly. So this is this with the sum. So these two on the outside with the sum. And then we'll enter this guy. So this is the state of the environment. And then what we can do is we can move the environment, this environment operator, uh, E naught E here, it doesn't act on the system degrees of, I mean, these are completely different spaces. So it'll go all the way through. And likewise, this E of K will go through. And then we'll have, once you push those things through, we'll have this operator, I mean, this number here. So this is, actually, no, this is an operator. So we'll have this operator here. Because what we're doing, we're kind of projecting these environment, we're projecting the unitary over these environmental degrees of freedom. So we'll do it on the left side and we'll do it on the right side, and then we'll define a new operator, LK. So LK here, if it's not clear from the notation, is just this guy. USE E naught. And this is some operator. And there's a question. The dimensions do not match. Not sure what that means. I mean, the dimensions are fine. Maybe you mean, let me see here. Maybe what you mean by that is the dimensions for this thing here. That's fine. That's why this is an operator. If this was, that's why this last quantity is an operator instead of just a number. And so, yeah, that's fine. That's why this is an operator instead of a number. So this just reduces U of SE I mean, you can think of USC as a big matrix, right? And whatever the dimension of the Hilbert space of SE is. And then I'm projecting onto some subspace of that and taking out these other degrees of freedom. So this is like this guy is just it's kind of like some submatrix of USC. So it's fine that, I mean, this vector and this thing don't need to be of the same dimension. I mean, this thing is still just some matrix itself. So yeah, that's why it's not of the same dimension. That's why this thing is not a number. It's an operator. Basis state is only defined on the unitary, so hopefully that answers that question. Another question, the unitary is defined on state and environment, but the basis state is only defined on the environment. Yeah, because I'm doing this partial trace, which is only over the environment. So I'm just introducing basis elements for the environment, right? And so I'm tracing those out. So I'm trying to get at the end of the day, you're trying to get an expression that's sort of independent of the environment in some manner. So I mean, it's not completely independent, but that allows you to describe the environment in the simplest possible terms. So this last expression is a nice way to do that. So what I have here is, because I don't have access to the system, now what I have is that I have the state of the system that's evolving into this quantum channel. and now I just have these operators here. So the evolution is defined entirely by the input row of S, and then plus these operators, which I've only sort of abstractly identified. It's a very simple like way to talk about a generic quantum channel because this is nice because this describes any kind of quantum channel whatsoever. This could describe a very complicated state of light going through a fiber or, qubit that a spin that's not just precessing but is like wobbling around. It can describe a cavity mode that's leaking out or whatever. But generically, any kind of quantum channel will have this decomposition. But usually, I mean, when you do it in practice, you'll have to know something about the environment in order to specify these Krauss operators. But this is a very useful decomposition. And like I said before, it's a bit formal, but just note that recall what we're doing. We can always describe evolution as a joint state of system environment. There's some unitary, and then all I really want to know at the end of the day, since I don't have access to the environment, is what the system is doing. And after I do some mathematical tricks, then what I have is this nice representation of that. Okay, so I have just some nice representation of it's called this Krauss rep. It's also called an operator sum representation because I have these operators acting on the state and I'm summing over them. So it's also called that. So another question, is the environment always separable from the system? It's a good question. Is the environment always separable from the system? Um,
Mm.
that's a good question.
Mm.
That's a really good question. Um, in practice, no. In practice, no. Um, in practice, no. I don't know. I mean, I would say that's a complicated question to answer. It's kind of like an initial value problem. Because yeah, it's kind of like an initial value problem. Um, is the environment always separable from the system? I mean, of course, I can always define this mathematically to be so. I can define that. I can say mathematically. I mean, it's easy to just say that and then be able to describe everything that you want to describe. But in practice, no. But that's a very good question. I'll just leave that open. Yeah. 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 Go have chat with, that's a good question. Ask, I bet they won't know either, but ask Chat GPT. They might have a good conversation about it. But no, in practice, no. But I mean, it's very close. But no, in practice, no. I mean, in practice, definitely not, because we have things that thermal equilibrium. We're kind of always starting from some system at thermal equilibrium with its surroundings, and so it's not really. But we try to cool things down. We try to initialize things properly. So it's fairly close. It's fairly close in many physical situations. But in principle, yeah, I can always write down at least things initially in that manner. Yeah, that's a good question. That's kind of like asking is are all systems independent or are they all correlated? Are they all in some joint state? So that's a good question. All right, next slide, please. Okay, channel evolution. What is this about? So let's see here. Oh, this is just a little bit more machinery with Krauss operators. So these operators that I defined earlier, these are called Krauss operators. These set of operators, LK. Um, if you want to, from now on, you can completely. I've written it here as this joint unitary, et cetera, with basis states. You can forget about that if you want. Okay. In practice, like, I mean, you can remember it just as an interesting detail, and sometimes it's useful. But the most important thing is the way that this channel is written in this operator sum form. The most important thing is the way that this channel is written, because for a lot of good channels, and we'll see examples of this. I'm just I can just give you, or someone can just give you, or you can just derive a Krauss representation for it. So you can just find Krauss operators for some noisy channel that you want, like photon loss in a fiber. So this is the most excuse me, important form here. And this is just yeah, so this is just a little bit of more technical details about Krauss operators. So, given this form of a channel, which again, I can always write them like this, is like, what do these operators actually satisfy? What do they need to do? One thing that you can show is that this is sort of like a completeness relation, is that when you conjugate and sum, that they sum to the identity. And this just comes from the original definition of the cross operator, and then the unitaries, U dagger U is identity. Okay. So that's just one relation that cross operators satisfy is this guy. And that also has that's also relevant that they need to do that actually also because um, the the output state should be normalized. So the output state of this channel. So remember, I said this is a valid state. So for any good state, so let me just say this first. Any good state, rho of S, its trace needs to be 1. So this is the equivalent of saying that all the eigenvalues sum to 1. All these eigenvalues are probabilities. This is conservation of probability. So probability needs to be conserved by this evolution in rho of S. And then if you do this trace explicitly for this channel, you can actually move some things around. So maybe I'll just write this out explicitly. Why not? Trace. Okay. Okay. Oh, no dagger there. Okay. Rho of S. Okay. Dagger. The trace is just a sum. So I can just pull this sum out. Trace LK rho S LK dagger. The trace is also cyclic. So meaning that now I'm going to write this up here. So trace of, for example, ABC is equal to trace CAB is equal to trace BCA. Okay, so using that, um, LK dagger. Okay. Rho S. Okay. Okay, good. So so we have this final thing here at the bottom. Let me change the color. Here at the bottom. Now we're saying that some of this completeness condition sums to identity, right? And so if you insert that into here, then what we have is trace. So you're just inserting identity for the sum, rho S, which equals 1. So we have that the trace of this output state is equal to the trace of the input state, and that's equal to 1. So it conserves the total probability. So that's one thing that these operators satisfy. Again, they also have to do other things. So that's this condition here. Actually, I have it written. Let me go back to red to make things clear. Go back to red. So I have this trace 1 condition. Density matrices are also Hermitian, which means their dagger is equal to them. And this is because I'll always have uh, this eigenvalue decomposition, and these eigenvalues lambda i's, they're just probabilities, so they're positive real numbers. And so, rho dagger is equal to, if I just dagger this, that means I just put a star on this. And these are real, so this needs to be equal to rho. Okay, needs to be equal to rho. And so you can show by this Krauss decomposition that this is certainly a Hermitian operator. And there's a few more, maybe two or more so conditions on states, but that are satisfied. Okay. Um, Another one, just little final thing, given two quantum channels N1 and N2, concatenation into N1 or N1 and N2. That, by the way, the order matters in general. That's also a quantum channel with its own cross operator. So I think in the lecture notes that I wrote, these are, you can play with those, and there's some exercises in there about defining cross operators for concatenation of channels. Okay, so let's move past cross operators. Next slide, please. Scratch, that's fine. Next slide. So that was a bunch of formal things. Here's some things in words about real world quantum channels and where they come out. There's just some pictures. So the top left this is like more of a controlled set of systems. This is like it's called cascaded quantum systems. So maybe I have some input mode A naught, and then I have some quantum processor here D1, and it does something to the input mode, and then there's some output mode A1, and maybe this D1 could be coherent, or maybe I'm doing some measurements or whatever, and then I'm sending it down the line to D2, et cetera, et cetera, et cetera. And so you can do do a lot of control and measurements and to tailor and engineer systems in this cascaded approach. Um, some other examples, like the bottom left, it's like maybe I have some input modes here. Maybe it's in optics, but then I transduce them to microwave, and I store them in some cavity, like a microwave cavity that I've drawn here. I'm not going to draw it twice. So that I've drawn here. Maybe I store it for a little while. Maybe I'm doing long distance transmission, or I want to do something on these optical modes, but I don't have full optical control. I need to do something with microwaves. So I'll transduce them to microwaves, store them in memory, maybe do some things, and then spit them back out, send them through this transducer. So this is like optics O to microwave, and then I'll transduce them again, and then I'll send them to a faraway location again in optics. And so again, you can describe all this globally by one big quantum channel, or by a concatenation of three different channels, etc. One of the simplest examples, and we'll go over this in detail, is photon loss, which could be through fiber or maybe even through free space, like a CubeSat. So, you send photons, and for the CubeSat, you're sending photons, a single photon in a beam, but maybe your collection device, your telescope, is only yay big, and so it's not collecting all the photons in the beam. You're only collecting a portion, and so there's some loss of your photons in that case, and you can quantify that and describe that loss by quantum channel. In fiber, you always have loss. This is the standard absorption law, like this Beer-Lambert law for dielectric materials, that the loss is exponential in the length of the fiber, and alpha is some characteristic length of the fiber that tells you how strong the loss is. So you can describe a photon transmission through a fiber, the loss, entirely by some parameter eta. Okay, so that's some physical examples. Next slide, Howie, please. Okay, this is more formal examples. Okay, so these are some typical things that come up in quantum systems, in qubits and at least single photons alike. The depolarizing channel on the bottom, that's more of a qubit thing. And this is sort of like a worst case scenario for a qubit noise is that, so for example, given some qubit psi, so this is, when I say qubit, I mean a two-level system. It's a superposition of 0 and 1, you know, at least the most general pure state is just like this. Beta. People typically write beta, don't they? There we go. Some pure state this. And with some probability, 1 minus p, nothing happens to the channel. But with some probability p, the output is just completely randomized. Okay, the output is just completely random. It's an identity. Everything about alpha and beta is completely lost, and this is just randomly mixed over this whole block sphere. Remember the block sphere? People draw a qubit on a block sphere. It's just completely random over the whole block sphere. There's no preferred direction. Okay, so all your information is more or less lost. And this is a depolarizing noise. It's a very simplified, simplistic, but very common noise model used to assess, like people use it all the time to when they're looking at when they come up with some architecture for quantum computing and they want to see fault tolerance, or they're looking at quantum error correction and they want to see some threshold stuff for their quantum error correcting codes. There's a question. Let
Here's
me
a
see.
question.
Why is P less than or equal to 4/3? It's because of there's an identity there. Um, psi has an overlap with the identity, and so P doesn't need to be just less than 1. Has overlap with it. So psi has an overlap with the identity. If you want to see more if you want to look at it in more detail, there's this book by and it's free online. So on the archive, there's a book by Mark Wilde where he introduces a bunch of these channels and he goes over the depolarizing channel. That's a good question, though. I had the same question when I was first learning this. But Wilde, I don't remember what year, but just look up Mark Wilde. It's an archive. It's on the archive book. He has 2 books. So, but this is a single author book, and he goes over a bunch of different types of quantum channels and their properties. But yeah, I mean, you can think a very simple reason why is that the output state psi has overlap with the identity. And so this can't just be, yeah, this can't just be that. Another example is an erasure channel. So in this case, like you send in a qubit, for example, or it doesn't even have to be a qubit, or a two-level system, but you send in some quantum state, and then it's completely erased. So it's like it's completely lost. And what here we do is we introduce an erasure state. So this is kind of like flags and tells you that, oh, your state is lost. And so if psi is in some Hilbert space, this erasure state sort of lies outside of the Hilbert space, such that now psi does not have support with this extra state. Okay, and this is called an erasure channel. And the erasure probability is less than or equal to 1 precisely. I mean, it's because of this condition that the psi doesn't have support on this erasure state. Let me resolve these questions real quick. Okay, good. And so, yeah, this is an erasure channel. Um, yeah, this is a common channel, and this is actually relevant when you're doing single photon stuff. So if you're encoding let's say a qubit into a single photon, basically the photon, like, and if you're storing the photon in a cavity, or you're sending it through an optical network of beam splitters and things, photon can be lost, of course, right? And so that photon loss, you can model it for a single photon, you can model it exactly with an erasure channel. So with some probability 1 minus epsilon, the photon arrives to you, and with some probability epsilon, the photon's not there. And the erasure state in that case is basically the coincidence of no photons. So either you get a photon and your detector clicks, or you don't get a photon when you expected it. And so that flags your erasure. Okay, next slide, please, Howie. Okay, I think this is some of the last bits about this messy business. It's oft, yeah, so unitary and isometric extensions. I don't think say much about this, but I will just mention it just because these are sometimes nice little formal things to know and little tricks that you can play if you want to do a bunch of theory. And so these are just nice things to know. So it's often useful to have different but equivalent descriptions of quantum channels. So we went over this unitary description before, okay, where you have some joint unitary acting, where you have some unitary acting on some joint system. But there's also so-called isometric extension, where I got this terminology from Chintao. It's like a lazy version of a unitary extension. This isometric extension, this is an isometry V. It's not quite a unitary, but it almost is. It's a lazy unitary. And so it does the V dagger V equals identity, but when you do the reverse, you don't get identity. You actually just you get some projection operator. What I mean by projection, uh, it's it's pi squared equals pi. That's what a projection. It's idempotent. It's the fancy word for it. This pi squared equals pi means it's idempotent. People call it idempotent. So in any case, it's not a complete unitary operator, but it's some isometry. And the isometry, that's sometimes nice because then you don't have to introduce this environment state and then, from the get-go, what you do is it's like you have some state rho s that just goes in this isometry, and then there's two outputs, right? So you have one input, two outputs. This is why it's not a unitary. It's 1 to 2. It's not 2 to 2. So this is why it's non-unitary, but it's close to it. And this is just it's just a useful thing sometimes. Okay, hold on. Uh, oh, okay. You're answering that highway. Okay, I'll let you answer that. Okay, next slide, please.
I think I'm stuck in the Q&A.
Uh,
Uh, well, does not allow me to.
you got it? Oh, okay. Actually, will you go back one slide? Just because we can answer this question directly. Back one more. Yeah, so somebody said, I guess you were about to answer them, but somebody said depolarizing an erasure channel seems similar to me, or am I misunderstood? You're misunderstood, but but like it's like understandably so. I mean, they look very, very similar, but the big difference again, and this is what I was stressing, is that the overlap with psi here for an erasure channel, right? The overlap between epsilon and psi is 0, whereas the overlap between psi and any state psi and identity, there's non-trivial overlap. And so that's the biggest difference is that this um, actually this whole thing here is in a bigger Hilbert space. So you're sort of taking psi, which is you're taking psi that lives in HS, and then you're mapping it to a state in like a bigger Hilbert space. HS cross, let's say the Hilbert space is like trivial, so it just contains one state, the erasure state. So it's a bigger Hilbert space. And here you're just staying in the Hilbert space. It's just you're randomized. You're kind of randomized. And that's why on the top you can flag whether you have an erasure or not. You flag it. Whereas the bottom, I mean, now you just have a noisy quantum state. Now you just have a really bad noisy quantum state. So yeah. Okay. And next one, next slide, Howie. Yeah, there we go. Why are useful? Are extensions and purifications useful? They give some, yeah, I'm not going to say much about this. I think when Chantal used to give these lectures, he would say a bit. I'm not going to say too much about this. I'll just say they're useful theoretical tools. Okay. They're very useful theoretical tools for quantum information analysis. Okay. Um, so here's like a sort of diagram, and an example is when people want to compute things like quantum capacities of channels, which is like the maximum amount of information you can transmit over some channel in. Okay, you see this maximization here. Then and so the quantum capacity is basically it's like the maximum number of bits you can communicate over a channel, quantum bits that you can communicate over a channel. Okay, it's important. And it's this sort of tools like purification and unitary extension are useful in actually computing things for a lot of different channels. Okay. I'm not going to go into details. I'm not really even going to define what this is. Well, let's see. Actually, let's look at the next slide and see. Will you go to the next slide? Yeah. So one more. Oh, actually, don't go one more. Don't go one more. Don't look. Okay. Sorry. Go back.
Okay.
Yeah.
Uh,
Will you go
I
back?
start. Oh,
No. Will you go back one? Yeah. Yeah, so they're useful tools. I'll just say it that way. This unitary extension and purification stuff are just useful tools, and I think it's also just interesting from like maybe a more philosophical viewpoint. This Church of larger Hilbert space that you can always sort of start from a mixed system and go to a large system to make a pure to have everything pure. I think that's interesting just from a physical perspective. Like if you think of small scale, maybe the state of the Earth is mixed state, obviously, because it's just sitting in a bigger solar system, then state of the solar system, galaxy, universe, and how far do we need to go? So I think that's just cool to think about. And again, it's useful into things. Um, okay. Somebody made a comment. Maybe you can, this is again about the erasure versus depolarizing. Maybe you can further decompose the identity operator into the Pauli matrices. Yes, yeah, you can. And for any single qubit state, you can also decompose that into Pauli matrices. So you'll see directly that things get mixed. If you write, actually, that's a good point. So you can decompose the identity operator into Pauli matrices just to make another point of erasure channel. Yeah, that's true. So if you took that expression for the depolarizing channel, you can actually write all of that in terms of Pauli matrices plus the identity, and you'll see that P needs to be less than or equal to 4/3. Okay. Yeah. I'm not going to do it, but you can write everything and then show that P needs to be less than or equal to 4/3. Yeah. So that's yeah. So you can decompose this guy into Pauli matrices plus the identity. Yeah. And of course, yeah. Okay. So I'll just say that. Um, hopefully that. All right. So next slide. So yeah, now we'll poll number two. Everyone wake up now. It's poll number two. Okay. So now we're gonna take some examples of erasure channel. And the reason is, again, this, erasure channel models photon loss for a single photon state. So we're going to look at erasure channel. So now we're going to think about two erasure channels. Okay. E1, E2, epsilon 1, epsilon 2. And we're going to send a state through two erasure channels. And so we have the concatenation of two erasure channels is another erasure channel. And with some erasure probability, epsilon 1, 2. So again, how I've defined it is epsilon is the probability that you lose the photon. right? So 1 minus epsilon is the probability that you keep the photon. Epsilon is the probability that you lose the photon. So what is the erasure probability epsilon 1 and 1, 2 in the case? 1, 2 for this concatenation of channels, right? So again, the erasure probability is 1 minus the transmission probability. Yeah, so this is the transmission probability, and this is the erasure probability. So yeah, for this question, what is the erasure probability? Epsilon 1, 2. Yeah, so how we started the poll, we'll give you guys about 70 seconds to answer, and then we'll close it. So again, the erasure probability is 1 minus the transmission probability. So try to think about what the transmission probability is to send through two consecutive channels. You guys got about 30 more seconds or so.
Yeah. 20 seconds left.
Okay, let's give another like 20 seconds.
Another, okay. 15 seconds left.
Okay, we're about to close it down, guys.
Yeah, time is up.
End it. Okay. I don't know if it is sharing the results.
Uh,
Well,
there-
most people said C. Few said A. Few said B. B is a bit understandable. A, that's like an average of probabilities, understandable. But will you click next slide, Howie? It gives an explanation. Yeah, so in this case, I mean, so the output, the first thing to think about it, to not get confused, is that the concatenation is of two erasure channels, just an erasure channel, right? So either the state gets transmitted or it gets erased. So we just need to, and the probability for transmission and erasure are related, right? So now we'll think in terms of the transmission probability. So the transmission probability for the first channel is just 1 minus epsilon 1, right? So I send it through the first channel and it goes through with some probability 1 minus epsilon 1. Okay. The transmission probability for the second channel is 1 minus epsilon 2, right? And these channels are independent. And so actually, it's just I just look at what's the probability that it was transmitted through the first, and then what's the probability that was transmitted through the second. And then the total transmission probability is just the product of probabilities, 1 minus epsilon 1 times 1 minus epsilon 2. Yes. And then so the erasure probability is just 1 minus the transmission probability. And so the answer is C. Cool. All right. Next slide, Howays. Okay, now we're going to look at, we've been a bit abstract, slightly more general with a few examples, but now we're going to look at specifically on Gaussian bosonic quantum channels. I'll describe what bosonic means. Hopefully you've heard it. And I'll try to describe what Gaussian means. It's the sort of simplest possible bosonic channels. So let's look at those. Okay, so bosonic, what I mean bosonic is maybe I mean several things, but the simplest thing is that um, just think of bosons as harmonic oscillators. Okay, so bosons are effectively harmonic oscillators, and yeah, we'll describe them in that way. So, for example, electromagnetic field, it's a bosonic field, at least the free electromagnetic field is a bosonic field described by an oscillator like Hamiltonian. So you've probably seen this Hamiltonian before. This is in some special units. This is x squared plus b squared type of Hamiltonian, and this is at some frequency omega. So this is just from free electromagnetic field and free space or even constrained to a cavity. And here we have the canonical position and momentum operators. For a physical oscillator that's constrained, actually here's a physical oscillator that's just clipped to a wall. It's on a spring and it can just vibrate. For a physical oscillator, Q is the position and P is the actual momentum, and they obey these canonical commutation relations. So hopefully everyone's seen these commutational relations before. So like this is what gives you Heisenberg's uncertainty principle and everything else. But for electromagnetic field, I mean, I still call them position momentum. Kind of call them just whatever you like. But everyone else calls them like quadrature operators of the field because it's like a sine operator and a cosine operator. So these are like the two quadrature operators of the electromagnetic field. Okay, so Q and P, position momentum, or these quadrature operators. But in any case, whatever you call them, they obey this canonical commutation relation. So we have some field, some quote unquote bosonic field or bosonic mode or what have you, and then or some quantum harmonic oscillator, and it's described by these operators QP, which satisfy this canonical commutation relation. You can write things differently, and this is how a lot of people like to use not QP, but they like to use A's and A daggers, where A's are the annihilation and A dagger, A is the annihilation operator, A dagger is the creation operator. When you first hear this, when you learn in quantum mechanics, you want to talk in terms of creation and annihilation operators because it sounds cool. But I like Q's and P's myself now that I've grown up a bit. But you can write everything in terms of annihilation and creation operators. They're just related to the Q's and P's in this way, and they satisfy this type of algebra. Okay, so this is a crash course on harmonic oscillator. You can also rewrite this harmonic oscillator Hamiltonian in this form. Okay, we're now I've defined some operator n hat, which is it's this. It's actually q squared plus p squared minus a half, something like this. Yeah, q squared p squared minus a half. And this is called a number operator. So this tells you more or less, given an eigenstate n of the Hamiltonian, so this number n, it's a positive integer. It could be zero, but it's 0, 1, 2, 3, 4, all the way up to however high you want to go. And n tells you the n operator tells you basically how many photons are in your state. I'm saying photons here, but it doesn't have to be photons. It could be some phonons, which are like a vibrational mode of some physical oscillator. Like for example, people play with opto mechanical membranes. It's like tiny little trampolines, and that the little trampoline have modes of oscillation. And when you cool them down really well, you can play with those, and there'll be some quantum oscillator. And you can describe the quanta of the oscillations by phonons, and you describe them exactly in this way. And so just to solidify the names a bit, given some number state or Fock state, Fock state n, it's defined like this. Remember, I called a dagger a creation operator because it creates photons or creates excitations. If I act with it n times on this vacuum state, which is like the state of no excitations, then I'll get n photons. And for instance, A annihilates photons, and so you see this relation, A acting on number state n takes you one down, while A dagger acting on state n takes you one up. And we always have this very important condition that the annihilation operator annihilates the vacuum, so we can't go below the vacuum. That's the last step of the ladder, or the first step of the ladder, whichever way it's the bottom step of the ladder. There we go. Okay, so that's a crash course on oscillators. Next slide, please, Howie. Um, then we'll scale up immediately to bigger and more oscillators, and yeah, harder things, more abstract things. And now, what we're going to try to get to is Gaussian channels. But you remember before we talked about quantum channels in the most generic case, and we talked about unitaries acting on a system and then tracing out unitaries acting on a system and environment, and then tracing out the environment. So we're going to take the same approach here. We're going to describe some large, basically oscillator system or modes of light. And then we're going to talk about Gaussian unitaries acting on these modes, and then we're going to trace them out in order to define bosonic Gaussian channels. Okay, and hopefully this will be a bit clearer as we move along. Okay, so first thing we can define to make things extremely compact. I know it's more notation, but if you actually play with this stuff in practice, on paper, this is some of the most useful kind of notation to use. It's extremely useful. So, we introduced these position and momentum operators before. So now we're going to suppose that we have N oscillators or N modes. Modes refer to modes of oscillation. So this could be different frequency modes. This could be different modes of a vibrating membrane. This could be in physical, like different springs or what have you. And so we'll have each one of those modes will have its own position and momentum operator. And we're going to organize those and write those compactly in some vector of operators, right? So this is some operator that'll act or that, sort of in some sense describes our quantum system, and then it's a vector of operators. And so maybe that's a weird thing to think about, but just think of the vector as just I'm just indexing different position and momentum operators here, and they obey some canonical commutation relations that you can write super duper compactly in this form I times this big omega. Again, this is just the canonical commutation relations, where now omega is some vector. I mean, not some vector, some matrix. This is called like a canonical form. This omega called the canonical form has a lot of relations to if you jump super into theory in terms of like classical phase space and classical mechanics, and people introduced canonical forms and canonical transformations and all this other stuff. In any case, just think about you don't have to think about this too much. You just say, oh, okay, this is some abstract way to write the canonical commutation relations. So now we have a system of bosonic modes. And what we'll think, okay, we have some unitary acting on some system of modes, and it's described by some parameter lambda. This could be time, this could be space, this could just be some parameter that I'm just giving you. And the unitary is generated by some Hamiltonian or generator H. Okay. And so when I say Gaussian bosonic channel, what I mean is the following. So a Gaussian unitary or Gaussian bosonic channel is where we can describe this unitary or this Hamiltonian by quadratic forms. So it's second order in the Q's and P's. What I mean by that is just some quadratic, so some Q, it goes like Q squared or Q times P or P squared or any kind of combinations, but it's only quadratic in the Q and P's. So this is what we call Gaussian bosonic channels. Okay. The reason we call them that is because it turns out that if states evolve under these Gaussian bosonic channels, then you kind of only need to describe the channel and other things by how it acts on first and second order moments of states. So first and second order, um, you only need to sort of look at um, things like the average of x or the average of x squared to describe how a Gaussian channel or Gaussian unitary acts. And so if you remember what a Gaussian is, it's completely described by its mean and covariance. And so in this case, Gaussian unitary Gaussian channels more or less just describe them by means and covariances with some caveats. So a non-Gaussian unitary is basically a unitary that is not Gaussian. So it's I should say also Gaussian unitary it can be quadratic. It can also just be linear. So it could just have a term that goes like Q. So right, okay. So a non-Gaussian unitary is any unitary that's not Gaussian. So it's like higher order. So Q cubed, Q cubed, Q to the fourth, or some nonlinearity in there. Um, so one very, very nice thing about Gaussian unitaries, and this is what makes them so simple, is that Gaussian unitaries result in linear evolution. So this is a Heisenberg picture here. So if I insert this operator, this vector of canonical operators x, and I act with it on some Gaussian unitary UG, the output is actually proportional to x up to some matrix multiplication plus some constant d. The constant d actually comes from if you have h that's linear. If you have h that's linear in the Q. And this could actually be done by coupling a quantum system to a classical system to induce this kind of transformation. But importantly, it's just this linear relation, and that makes things very, very simple. So S here is just some matrix. Formally, it's some real symplectic matrix, which comes with its own things, but I'll just say it's just some matrix S. And then the vector D is just it's just some real vector. Okay. Next slide, please, Howie. Yeah. Yeah, okay. So this is an example. So this is I think so I'm going to go over a few important examples of um, Gaussian Hamiltonians, Gaussian unitaries. And one very important example, probably one of the most important examples, is displacement operator, and that's something that's linear. That's the Hamiltonian that's linear in QMP. And so in terms of A and A dagger, you'll often see it written like this. In terms of QMP, you can write it in this manner. And if you put the H in exponential form, then you have this unitary displacement operator, e to the IH. And why do we call this displacement operator? The reason is because if we act on it onto the A hat, onto the annihilation operator, it just displaces it by constant. Okay. Similarly, if you act on position, it takes position to just displaces the position. Okay. Um, So I'm not gonna go through any mathematical details about it. I'm just gonna state some properties of it. So one thing is that you can think of it like displacement sort of produce coherent states from the vacuum. Coherent state is like the quantum state of a really, really good high quality laser. And so a displacement operator acting on the vacuum state produces a coherent state. I mentioned this before, but physically, this is like you have some really coherent macroscopic classical current that's coupled to an electromagnetic field with zero population at time t equals zero, and then you turn it on for a while, and the current induces this displacement on the field and generates a laser state, which is in a coherent state. There's a multi-mode version of this. It does similar things as the single mode version. It just takes x hat and this vector of operators x, and then just adds some real multi-dimensional vector to it. That's about it. That's why this notation is very useful. Vector of operators is that Gaussian stuff. You can write them very simply in this form. One very important thing about these set of displacement operators is more of a mathematical thing again. Um, they form an operator basis. So this is similar to qubits. If you have a single qubit, the Pauli matrices plus identity form like an operator basis on the qubit space. These displacement operators also form an operator basis on this n-dimensional bosonic space, and they form it in this way. So this is sort of the operator completeness relation for them. And so again, this is analogous to Pauli's. Okay, next slide, please, Howie. So that's a displacement operator. Um, here's some more stuff with describing bosonic states and using displacement operators. So recall what I just said that let me also say one thing. I'm very tangentially going over a bunch of this Gaussian stuff and oscillator stuff, but there's two really good references if you want to look further into these things. I sent out some notes that have a bunch of references and that have these references on it, but I'll just state it here also. There's a book called Quantum Continuous Variables by Serafini. Okay. It's actually a small book, and so it's quite nice. And he has a bunch of worked out examples. So he doesn't have exercises for the reader. He has exercises for the reader, but then he gives you full solutions to it. So that's how I learned it. I think that's one of the best ways to do it. Just
Yeah.
like show me what to do first, and then I'll go solve my own problems later. So that's actually that's Quantum Continuous Variables by Serafini. That's a good book. There's also a review article. It's actually a really good review article. It's probably one of the better review articles I've read. Gaussian Quantum Information Theory by Wiedbrook and others. This has more of like a quantum info flavor to it. Or I think Serafini's, so et al. And others. I'll just put a plus sign. So these are two good places if you want to learn more details about Gaussian stuff, um, anything Gaussian, and would actually prepare you for research. So if you wanted to go that route. Okay, so in any case, now we're going to talk about describing Gaussian states by characteristic and Wigner functions. So recall that, as I said in the last slide, that these displacement operators, they form a basis. And so because they form a basis, we can sort of expand any operator or state in terms of the displacement operators. And this allows us to define so-called characteristic function for any operator A. Okay, so we have some operator A, and because of this completeness relation, we can expand the operator A into this displacement operator basis. And by using this completeness relation up here, you can show that this characteristic function is just defined in this manner. So it's just the trace of a displacement operator times the operator. And finally, so if you take a Fourier transform of this characteristic function, you will find the so-called Wigner function of an operator A. Okay, so a lot of people talk in terms of Wigner functions. You can actually use this to describe like even classical systems, like mixed states of classical systems. So you have, this is like in statistical mechanics, if you guys have taken statistical mechanics and you look at mixed states of oscillators and phase space and Q and P space, this is more or less what the Wigner function is. And this is useful because one can define a quantum state and speak in terms of functions like characteristic and Wigner functions rather than some density matrix. So this gives you like a different picture of a quantum state. Practically, you can also do quantum state tomography. So you can measure Q's and P's and slices of Q's and P's along some, this is like Q, this is P, and you have some, state described by some Wigner function. You can do Q and P measurements and perform quantum state tomography and to map out the Wigner function in phase space. Okay. Okay, next slide, please, Howie. I think that goes into this a little bit more. So these are just some examples. So on the left, this is the Wigner function. So the horizontal, the sort of the XY plane, that's the QP, and the vertical is the value of the Wigner function. Okay. So for the left is a vacuum state. If you notice, it's symmetric and it's Gaussian. Okay. So any Gaussian bosonic state will actually just be a Gaussian in phase space. Okay. So this is just one mode. And so yeah. So it just has two degrees of freedom, Q and P. And then so we have some joint uh QP. And for Gaussian, it turns out that this Wigner function is always greater than or equal to um, 0, and then up to some scaling factor. It's like bounded by 1. But this is a Gaussian probability distribution. For Gaussian states, the Wigner function is a Gaussian probability distribution. Okay. And so, yeah, that's why they're called Gaussian states, because in phase space, they're represented by Gaussian functions. A counter example of that is a single photon state. So this Fock state of n equals 1. That's on the right. Actually, any Fock state. So these are inherently non-Gaussian states. And the reason they're non-Gaussian states is simply their Wigner functions are not Gaussians. And their Wigner functions can take on negative values. Okay. And this is actually implies non-Gaussianity when their Wigner function. I mean, this is kind of like one definition of non-Gaussianity. Wigner function take on negative values. So sometimes a Wigner function and characteristic function and these other things are called quasi-probabilities, because in some cases you can say that the Wigner function genuinely is a probability distribution, like for all Gaussian states, but in other cases it's not quite, right? So for this single photon state on the right, it has negative values, and so it's not a proper probability distribution in general, but it's a quasi probability distribution. Okay, clear. Okay, so what else? More about characteristic and Wigner functions. Okay, so this is how they transform under Gaussian unitaries. Again, this is kind of why we like them, is that now instead of this is why we like Gaussian evolution, this is why we like Wigner functions, characteristic functions, is because now instead of acting with operators on states and asking how does some complicated density matrix transform under, unitary evolution, we can talk about how a function transforms under linear transformations. Okay, like this, like how a function, like the Wigner function or the characteristic function, transforms under some matrix multiplication and displacements. So it's very useful. So, for example, so this is characteristic function, and this is very useful. And so here's how do I want to say this? Let me find where did my thing go? Okay, there we go. So if we have an initial, whoa, why are you doing a line? Free draw. Just free draw. Okay. If we have some, let's say we have a characteristic function of some operator A, okay? And now what we'll do is we'll say, what's the characteristic function of the operator A um, after acting with a Gaussian unitary? Okay, so that's what this guy is, characteristic function after evolution of the operator A. Well, it turns out that, and so recall, so this C here, that's just it's like some random variable. Okay, that's C here. This bold script here is just some random real number variable. Oops. And so what's nice is that the characteristic function after this Gaussian evolution, um, this is sort of like an operator evolution, but it turns out that after a Gaussian transformation, that we can equivalently just act on the random variable by some matrix S and then multiply some phase. So now everything is pushed again to these real numbers C, and everything's acting on these real numbers C instead of the operator. Similar thing holds for Wigner function. Uh, so hold on. So let me answer a question. Someone said, I am new to this concept, so I'm a bit confused. What's the role of A during forming the Wigner function? The Wigner function is it's something that describes A. Characteristic in Wigner function is something that describes A. So, like the characteristic function C A hat is defined through A and displacement operators. So it's defined as displacement operator where you displace by C, C, and then times this function A. So it depends on A and it depends on this real displacement C. So that's the definition of the characteristic function. And then using properties of the displacement operators, it turns out that you can write any operator in terms of a displacement. Maybe there's a dagger here. And then the characteristic function of the operator itself. And so that's why and then the Wigner function is just the Fourier transform of that. So it's just some integral. So what's the role of A during forming the Wigner function? Um, the Wigner function is a function of A. So yeah. And all this to say, and all this is just to say is that the interpretation, and this is exactly why, this is how I always think of them, is that the interpretation is that a Gaussian unitary is just a linear transformation in phase space and like real phase space. So a real phase space, like this C is in some real phase space for n mode, it's in a real phase space, like a real space of 2 to the n. And then Gaussian unitaries, because it acts in this way by just doing displacements and linear transformation and matrix multiplication, so the Gaussian unitaries really just correspond to linear transformations in a real phase space, in a phase space of real variables. So that's why they're so nice and so useful and so easy to explain them. Okay, next slide, Howie. So these are further examples. I think we'll give a few of these and then move on to channels finally. I think we got about an hour and 15 minutes left. Okay, so we'll go for about 15 minutes, then do a break. So phase rotation, the Hamiltonian in this case is just the number operator or just the free Hamiltonian, and this just generates rotations. So if I have a vacuum state here. So let me just describe this picture real quick. What I have is a P on the vertical, Q on the horizontal. This is like a Wigner function picture. So it's like the Wigner functions that I drew before, but now it's like just a projection onto the Q and P plane. So remember, I had this 3D like Gaussian before. So this is like a projection of that onto the plane, like a slice of that. Okay. It's like a slice of that. Okay, so phase rotation, all it does is it takes some initial state and it rotates it by some angle phi. So for example, this model is like free propagation in a fiber, where now the phase phi is just k times L, where L is the length of the fiber or propagation length, and k is the wave number of the mode. Linear transformation, you mean affine linear? When I say linear transformation, I mean some I mean, this is what I mean. some linear relationship between the input and the output. And it is parameterized. So there are some affine parameters associated with S and D. But it's a parameterized linear transformation. Okay. So that's a phase rotation. Next slide, please, Howie. Single mode squeezing. There's another important one. Squeezing is something that's used by LIGO to enhance the sensitivity. So it has a Hamiltonian of this form. So it's a Q times P sort of deal. And what it does is that when acting on Q, it squeezes Q, so it makes Q smaller, reduces Q by e to the minus R. But in accordance with the Heisenberg principle, it must amplify P in order to make sigma Q sigma P. What is it? A half? Is that right, Howie? Or is it square? Is it supposed to be sigma
Yeah.
squared? I don't remember. It's like a half, but what? Yeah. Here, I'll use my favorite notation actually. Here, I'll use my favorite notation. Squiggle. Squiggle goes like one, right? Sigma Q, sigma P goes like one. Okay, so in order to obey Heisenberg uncertainty, if it squeezes one quadrature, it must amplify the other. And so this is an example here is we have some vacuum state. Recall I showed vacuum earlier, and we squeeze one quadrature that actually takes it to a squeeze vacuum state. Okay, so one quadrature is squeezed, and so you can actually get a large, I mean, a very, very good precision of like if this is the position, you can actually get high resolution and estimating precision and estimating position here along the squeeze quadrature. But this other part is amplified. Okay, and again, this is what LIGO does to enhance its sensitivity. Someone said another question. I thought it is only linear if and only if d equals zero. Um, I mean, you will, yeah, I mean, this is semantics thing. Um, I mean, you can demarcate between the d equals zero and the d not equal zero case, but yeah, I mean, this is that's like changing a coordinate system. Um, yeah, I mean, changing the origin of your coordinates. That's what taking d non-zero means. Okay, next slide, please, Howie. Try to wrap up some of this Gaussian stuff. Very important Gaussian unitary is the beam splitter. And so this has the Hamiltonian up here. So this is a interaction between two different modes or two different oscillators. And what it does is it conserves particle number. And the reason it does this is that if you just look at the interactions, annihilates a photon in the A mode, but B dagger creates a photon in the B mode. So basically, what you have is you have a photon in A leaving A and then going to B. Likewise, the inverse process is also there. So you have B losing a photon and going to A. Okay. And so that's that trend. So it's basically two modes swapping quanta. Um, In terms of like optics, you can think of it in this way instead. So the unitary, if you parameterize it by some theta, the unitary acting on A gives you cosine theta times the input plus sine theta times the input of the other mode. And similar thing for how B transforms. And this is just like a simple linear optical transformation that you might have seen before in some optics courses. And so here eta is, cosine squared is the transmission probability. So if I draw a physical beam splitter here, the probability that B just transmits to B prime is eta. And this, again, this is just coherent exchange of quanta between the two modes. Next one, two-mode squeezing, another staple of quantum information processing with light, a fantastic operation indeed. So this generates two-mode squeezing is something between two states. This is not a passive linear optical transformation, but this actually generates light, generates photons, and in particular generates photons in pairs. Okay, so here, if one photon is generated in A, one is also generated in B, and likewise the inverse process, loss. And so a two-mode squeezing transformation has does this on the modes. If you notice these important daggers here that were not there on the for the beam splitter. Okay, so yeah, this corresponds to actually particle creation or photon creation, and people do this with crystals or whatever. And so we also sometimes quantify the amount of particle creation by this cosh squared R. So this is the gain. And yeah, importantly, this can be greater than or equal to one, where if you recall from before, from the previous slide for a beam splitter, we have some transmission probability that's less than one because it's a probability, but this is actually a gain. So if you input some, yeah, if you input some light here, it'll be amplified with some gain G. And again, this corresponds to particle pair creation and also generates a so-called two-mode squeeze vacuum state starting from the vacuum, which is an entangled state and is useful for communication, sensing, all kind of deals. And also has some nice physical things that people care about. Okay, next slide, please, Howie. I'll go back one. I'll just put a little tidbit. Yeah, I say particle pair when I say particle pair creation. This is sort of like it's not really a quantum information. People don't think about it like that in terms of quantum information processing. But if you speak to someone in like quantum field theory, they'll say it in this manner. Okay, they'll say particle pair creation because this stuff, a similar thing comes up in like quantum fields and curved space and a bunch of fun stuff there. So similar types of transformations happen. Okay. Um, We're still on the unitary stuff. We'll go for about 5 more minutes before a little break, and we'll see how much I can get if we can actually get to the channels. But just briefly, so that was basically all the Gaussian unitaries that we wanted to cover. We looked at displacements, just shifting things. We looked at phase rotation. That's just, taking something in phase space and then just rotating it about some angle. That's like free evolution. Looked at beam splitters, which is just exchanging quanta, and we looked at squeezing, which amplifies one quadrature and squeezes the other, reduces the other. So those are all Gaussian transformations. I'll just say briefly right here about non-Gaussian unitaries. Okay. And this is based on a higher order Hamiltonians, like I mentioned before. And so this automatically means that some like nonlinearity is required. So you need to couple the field to itself at some higher order, or even couple the field to possibly like like a discrete system, like a qubit system, in order to induce a nonlinearity on the system of interest. Some examples include the cubic phase gate and this Kerr nonlinearity, which goes like n squared. The Kerr nonlinearity, this happens in optical materials, like nonlinear optical materials. Kerr nonlinearity, this goes like n squared. So this actually goes like n hat goes like the field squared. So this actually goes like the field to the fourth power. So Kerr nonlinearity would happen in like these so-called chi3 nonlinear materials. Okay, but you need some nonlinear material, not just a dielectric, in order to induce a Kerr nonlinearity. So let me say, what else do I want to say? Oh, one important thing, and this is why we actually need to go beyond Gaussian systems in practice, is that it turns out that non-Gaussian elements are actually required for many important quantum information processing tasks. So for example, if you wanted to do quantum error correction, or you wanted to build a fault-tolerant quantum computer out of bosonic modes, that is resilient to Gaussian errors, then you need some sort of non-Gaussian elements. So this could be either at the level of states, so you need non-Gaussian states, non-Gaussian operations, or you need some non-Gaussian measurements in order to build fault-tolerant quantum computing with bosonic modes or do bosonic quantum error correction. And people do this nowadays pretty routinely, especially in superconducting circuits, where they'll couple a two-level system like a transmon qubit, which I depict here, and they'll couple it to a mode of like a microwave resonator to induce non-Gaussian transformations onto the state of light in the resonator. So, yeah, that's all I wanted to say there. Next slide, please, Howie. Okay, so now we're finally getting to the Gaussian channels. We can go ahead and take a short break, and then I'll finish off with some Gaussian channels. Hopefully it won't take too long. So we'll take what we learned from the unitaries, Gaussian unitaries, and then try to construct like Gaussian quantum channels. Remember from the beginning, we were talking about quantum channels, and now we want specific quantum channels that are important for light propagation and things. So we'll move on to Gaussian channels. But before that, we'll take maybe a 10-minute break and come back here. I don't know what time it is for you guys, but it's 3 o'clock for me in Tucson. And and we'll convene in about 10 minutes. So everybody get some water, use the restroom, do what you need to do. See you in about 10 minutes. Okay, so it's been about 10 minutes. Hopefully everyone's trickled back in or close to it. We'll give it about another minute or so if anybody's falling behind. 3 hours a long time for for a lecture. I've been talking for about 2 hours, so yeah, here in a little while, here shortly, y'all be able to hear Howay's voice instead of mine, listening to Howay instead of me for the next hour. So I'm gonna try to wrap this stuff up pretty quickly. Okay, so let's get started. Um, Now we're going on to Gaussian channels. If you recall from the beginning, sort of the flow was that we originally, in the very beginning of the lecture, we started with some, uber evolution by some unitary operator U, and then in very abstract way, in general way, we said, evolution of a quantum system under some unitary evolution by, of some system and environment. And if you just look at the system by itself, because in practice all we have is the system, not always have access to the environment, is that we can describe the evolution on the system alone by some generic quantum channel n. So now what we're going to do is we're going to take that same idea but apply it to this class of Gaussian channels. Okay, and there's certain Gaussian channels that are nice. So now we're going to apply we restrict ourselves to Gaussian unitaries UG, those displacements, beam splitters, squeezers that we talked about before. But now we're going to think, oh, the Gaussian channel is acting on multiple modes of the system. So maybe we have some beam splitter on multiple modes, some two-mode squeezer on multiple modes, but maybe we only have access to one mode. And so then that leads us to the notion of a Gaussian channel. Okay. And the most prominent, most important Gaussian channel for, for photons, especially for photons, whether they be microwave, whether they be optics, whatever, whether you're doing communication or computation, or you're trying to do some sensing with some microwave resonator or what have you, one of the most important channels, period, is the so-called thermal loss channel. Okay. Why is this important? It's just so physical. It's so physical. So we'll say a thermal loss channel is we'll notate it by this is represented by two parameters, eta and ne. And so what a thermal loss channel is that we have some thermal environment. So you can think of like the sun here, or it's just some, the thermal photons in a chaotic room, but we have some system and some pristine, quantum device. And so we have this thermal environment effectively interacting with our interesting mode on a beam splitter. So the interesting mode is here, is A, the input A. And then we have some thermal environmental mode, E, interacting with that, our interesting mode, A, on a beam splitter. And again, one physical example is we have, for instance, like a microwave cavity, which houses some photon in it, right? For a perfect cavity, these walls are completely conducting and no photons can leak out of the cavity because basically the electromagnetic field at the endpoints are zero and there's no way for the modes to get out. But in practice, this is never the case. The walls are always slightly absorptive, etc. And so it's not quite zero, but we have some evanescent decaying. And then due to that evanescent decaying, modes can leak out into the surrounding environment. Not only can they leak out, but things can leak in because of that, right? It's like a two-way sort of process. So we can have some thermal chaotic photons leaking into our device. So that's physically what it represents. is loss of a photonic mode and leaking from these environmental modes. But in principle, this is really easily described by just some environment mode interacting with our system mode on a beam splitter. So it's quite nice. And in the simplest case, it's described in a Heisenberg picture as follows. So the output is a function of the input plus some environmental mode E. And eta here is basically the probability to transmit through this quantum channel. Okay. And E here we'll take to be some thermal state. And when I mean thermal state, there's a lot that I mean by this, but you can think about it as it's completely characterized by one single number, and that is the and one moment, one number NE, which is the number of photons in the state, and one moment, which is the second moment here. So a quadratic product of A's and A daggers. All higher order moments like e to the 4, e to the 6, whatever, can always be written as a product of second moments. Okay, so for example, e e dagger, e can always be written as products of this second moment. So yeah, this is a Gaussian approximation for the environment. Okay, so that's the thermal loss channel. Okay, so it's very simple how it's described, but it's extremely useful. You model fibers this way, and so in this case, you send a mode through a fiber and interacts with the atoms, with the vibrational modes of the fiber, and perhaps it's that's A, and perhaps that's some of it's scattered in the fiber and absorbed by the walls, and the output is then A prime. But in any case, you can describe the evolution pretty well by the simple Heisenberg relation. Okay. Next slide, Howie. Um, Pure loss. Oh, okay, so this is a nice little question. Okay, so um, yeah, so we had a thermal loss channel before. Actually, let's go back just one more, please. One more slide if you go back, because I mentioned pure loss here. Okay, so I say this is a thermal loss channel. A pure loss channel is when the environmental modes are approximately vacuum. So NE here is it's like the temperature so low, or you can think of that the frequency of the fields are so high, like in optical frequencies, that the background population is zero. And so that's what people call a pure loss channel, is when really the only thing leaking in here is the background environment. It's not a thermal state. It's just vacuum fluctuations. Okay. So that's clarified. Next slide, please. So move on to this poll. Okay, so a pure loss channel, so that's Ne equals 0, no thermal photons, has an operator sum representation as follows. Recall the Krauss representation decomposition that we mentioned at the very beginning of the lecture. So this is a operator sum representation. It's a Krauss decomposition for a pure loss channel. Okay. And it just turns out that there are an infinite number of Krauss operators for, you just have to deal with that when you're dealing with bosonic modes. Okay. And and it turns out that the Krauss operators for a pure loss channel are described by these very complicated things. The reason it's so complicated is just because we're dealing with this large dimensional Hilbert space, and things are non-trivial. In any case, though, this is the Krauss operators for this. So the question is, how many Krauss operators do we need to describe the output for a single photon input state? Okay. So how many Krauss operators? So we'll give you a bit more time on this one, maybe close to 90 seconds or so. But now Now look though, be careful when you're answering this question because the sum runs from L equals 0 all the way up to L equal infinity. So you have to consider the L equals 0 term, consider it term by term, okay? And only focus on this part of the annihilation operator part, okay? And think about what each of these L, terms do to a single photon state. Recall that, A hat annihilates a photon, okay? And then look at this term by term. All right. And then ask yourself, how many of these terms do we actually need to describe the operation of this channel on a single photon state, starting from L equals 0 to L equals 1 to L equals, etc. We'll give about a minute more. Yeah, I'm getting a snack when it's your turn. I'm gonna get a snack. Eat some pecans or something. Okay, we'll give about 30 seconds more, guys. And then only 17 people have participated, 18. So go ahead and get your numbers in. All right, 10 more seconds. And that's it. Okay, so I'm gonna finish it. In poll, about half people said two, quarter people said one, a quarter people said three. It's a bit tricky. Yeah, I can understand the A, people saying A, but that's not the correct answer. The correct answer is B. If you'll hit the next slide button, give an explanation. Yeah, you need the first two. And that's why I was trying to give the hint about this sum starts at L equals 0. So at L equals 0, if you take the zeroth, you know, exponential 0 of anything is just 1. And so the zeroth term doesn't annihilate there is no annihilation operator. So you need at least need that one. Okay, so you do need that one. But then the next term, this is L equals 0. And it goes something like 1 times whatever all this mess is. With the L equals 1 term, it goes something like, whatever all this mess is, times A hat times one annihilation, right? And the single photon has one photon. So this will annihilate one photon and then give you back something else. And higher order terms, so for example, so let me say that differently. So if you have a single photon state, an annihilation operator acting on a single photon state, then that will take you to the vacuum state, right? Now, higher order terms, so L equals 2 will go like A squared. That's two operations, two annihilations. Um, so we'll get A now. The first annihilates the quanta, and then we'll have annihilation operator acting on the vacuum, but that's just 0. Okay. So we don't need the L equal 2 term. We do need at least both L equals 0 and L equals 1, right? So we do, the answer is 2 here. And so only the first two Krauss operators are necessary. And if you go through this by acting on a single photon state, then they're just given by these representations down here. Okay. Next slide, please, Howie. A second, and we'll come back to the thermal loss channel too. Hopefully it will end pretty quickly though. I think it does end soon, at least my portion. Okay, so another important example of a Gaussian channel is a thermal amplifier channel. So instead of losing photons, you have some amplification. And so in this case, what we actually have is we have some thermal environment interacting with a with some mode. So we have some system mode A, and we have some environment mode E. And so we have the thermal environmental mode acting with our system via two mode squeezing. That's supposed to be two, not toe mode squeezing. Via toe mode squeezing. And so this actually models linear phase insensitive amplification, so noisy linear amplifiers, right? So the transformation in this case is just the square root of the gain times the input plus this environmental piece, all right? And so yeah, this actually models a linear amplifier. And when the environmental mode is in vacuum, when N equals zero, this is often called a quantum limited amplifier. So you'll see that in the literature a lot. You'll see that in papers a lot. You'll see that everywhere. People using quantum limited amplifiers. There's actually a very big technology to amplify very weak signals is to do low noise quantum limited amplification. Okay. Okay, next slide, please, Howie. Um, The last one that I want to consider, I think how much time do we have left? We have 30 minutes left, I believe. Something like that. Probably.
Our schedule extends to 3:30, maybe 4:30 actually, right?
Oh yeah, yeah, okay.
Uh, Not sure.
Okay. Okay, so let's just move forward. So the last example is an additive Gaussian noise channel. And so there's two examples from before. I said one corresponds to like a beam splitter with environment, one corresponds to a two-mode squeezer with an environment. Additive Gaussian noise channel is pretty interesting. Actually, the only thing you're doing there is adding thermal noise to the input. This model is actually like a random walk in phase space or like fluctuations of a classical drive. So the transformation in this case is you take A to A plus some real number C, where C is some random variable and it's thermally populated. Okay. So actually what this corresponds to in terms of a channel is that you have a displacement operator acting on your input dagger, put a hat, uh, and there's random displacements happening on your input under some probability distribution P, where this P has a variance that goes like any. So that you just randomly, that's why it's kind of like a random walk or fluctuations of a classical drive, like a classical drive field you can describe by, displacement operators, coherent states. And this is where your drive has some random component, C. Okay. So that's an important operation too. Okay, next slide, please, Howie. Next slide. I won't go over this much, but you can also, you can talk about Gaussian channels and concatenation of Gaussian can or cascaded quantum channels. So, for example, you can describe, oh, why does it keep doing that? You can describe cascaded lossy devices. So maybe you have some input and you send through one lossy device and then it does some things in the middle and then it goes through another lossy device and you can ask it what happens. So for example, a concatenated channel of two loss channels, two thermal loss channels is also a thermal loss channel. Okay. And now the transmission probability is just a product of probabilities, the product of transmission probabilities. I won't go through the derivation, but you can do it doing you can provide the derivation um, in the Heisenberg picture as before. Maybe I'll briefly do it. The output from the first loss channel, you remember the unitary extension, this unitary extension where we go to bigger Hilbert space. This is just a beam splitter with an environmental mode that's populated in a thermal state, E1. Okay. And then you send that through another one with eta 2 and E2. And so then you have an output A prime prime is equal to eta 2 A prime now plus 1 minus eta 2 1 minus E2. And you can show that that equals a sort of thermal loss thing with these kind of described by these kind of parameters. Okay. So you can do all these things in the Heisenberg picture, which are very nice, and how they act on annihilation creation operators. Okay, so next slide, please, Howie. Um, this one's much more involved. I think this is described a lot in the notes. Actually, I have full derivations in the notes that were hopefully sent, but if not, we can also send them afterward. This is, for example, this is a bit tricky one. So this is like if you look at the diagram here, this is you go through a loss channel first, and then you go through a thermal amplifier channel. So it's like you send light through a fiber, it gets lost, some of it gets lost, but then at the output you want to amplify it so that you can measure it. Okay, so this is typical in like classical optical systems, right? You send them all maybe something over a long transmission line, and then at the output, maybe you want to send it over you want to send light over very long distances. You send it for a while, some of it gets lost. There's an amplifier in the middle. You amplify the signal, and then you send it again, goes to another amplifier, et cetera, et cetera. And so this is an example of loss and then amplification. And that one's pretty interesting. This concatenation, I'll just say very briefly, because depending on the values of the amount of amplification and the amount of loss, this turns into this can be three different channels. So basically, if the gain isn't that high, so it's more or less less than the loss, then the resulting concatenated channel is a thermal loss channel. Okay. Now with a loss parameter G times eta. So G times eta is less than 1. If the gain is pretty high or the loss is relatively low, then it turns out that the concatenated channel is an amplifier channel. So it's a thermal amplifier channel with a gain that goes like G times eta. And then there's a critical point in the middle, which is interesting. Whenever the gain and the loss are completely balanced, and it turns out at that point that the output channel, I mean, the resulting concatenated channel is an additive Gaussian noise channel. Um, so that's pretty interesting. So that's actually one way to think about the additive Gaussian noise channel is that its purification is beam splitter transformation followed by a two-mode squeezing operation. Okay, next slide, please, Howie. Okay, so this is an exercise. It's not a poll. This is an exercise that yours truly, Anthony Brady, is supposed to go over in detail. So let's go over this in detail and see what we have. Okay, so let's read this from before. We have that. So I claimed that a additive noise channel in B1, it can be thought of as a concatenation of loss and amplifier when the gain and the loss obeys this condition. And then the amount of thermal noise added from this additive noise channel has some specific form. And then what I want to do is to show that actually if I reverse this order of the amplifier and the loss, so let's say I want to amplify before I do loss rather than after, okay? Oh, so yeah, first thing I want to show is that if I reverse the order that I actually get an additive noise channel, okay? So yeah, so let me clarify. This first bit is lost and amplify, okay? And I said before, this corresponds to an additive noise channel. Now let's say I switch the operations, and then I want to show that this also corresponds to an additive noise channel, but with a different amount of additive noise in B2 rather than in B1. And then I want to prove actually that the amount of noise in B2 is less than in B1. So what this tells me is that actually if I do amplification before loss, that's less noisy than doing loss in an amplifier. That's kind of like saying actually amplify your signal before sending it through a lossy channel. Okay. Okay, so let's see. How does this go? We prove at the level of creation and annihilation operators. And so what we're gonna do is we're gonna show this relation here. Okay. So remember the transformations, it goes something like a two-mode squeezer between an environment mode and the input. And so first we send this through we do the two-mode squeezing, we have some gain G, and then we have this environment mode. All right. And then what we'll do is we send this A prime through a loss channel, and the output is this. This is just the two mode. I mean, this is just the beam splitter transformation. Um, uh, Correct. And then what you can do is you can input this relation into here, and then write it in a very suggestive form. Okay. What you do is once you input A prime into A double prime, and you will separate all the terms which go like A. So we'll separate all the terms which go like A. So you'll notice here there'll just be one A. So G times eta, that's this first term. And yeah, and then couple bring all of your environmental terms together. Okay. And so that's what I've done on this side. And then what happens at A to G equals 1? So this is the tricky part. So at this point, it's not clear that it's an additive noise channel. But then as you take A to G goes to 1, you can see that obviously A prime goes like A plus some, you know, plus some bits here, right? And yeah, I mean, the important part is that it's exactly this. A prime goes like A plus some bits here, and those bits here will just be some random will be some random variable because these E2s and E1s are chaotic. And yeah, so let me look in more detail here. Yeah, that's right. Okay. So then what we can do, for example, let's say we want to compute the amount of noise that are added to this channel in B2. What we can do is we look at A prime prime dagger, A prime prime, and we'll take the expectation value. So this is the number of quanta in the output. Okay, so this will go like A to G, A dagger A, plus all these modes are independent. And so they're the number of quanta just add. So I have A to G minus 1. Um, E2 dagger, E2 plus 1 minus eta. Um, and then what? E1 dagger, E1. And this is just whatever the input is. And then this is, note that this is in 2. This is in 1. And we'll also take eta G goes to 1. Eta, actually, I'll write it even more suggestive way. G equals 1 over eta. So this is just whatever the input was, plus G equals 1 over eta. So this is eta 1 over eta, we have 1 minus eta over eta. That's what this equals, times this is just N2 plus 1 minus eta N1. And that gives us what I have already wrote down for, oh, actually, I made a mistake here. I wrote down E2 dagger E2, but it should be E2 E2 dagger right there. And so actually this is N2 plus 1. Great. N2 plus 1. Great. And that's where this plus 1 comes from. Okay. And so that gives us NB2, and it's that. And then yeah, so that's that. So let me just let me do a different color now. Let me do this in blue. So now we've computed NB2, and if you look at NB1, it's very similar. All you have to do is compare those, and you say NB2, put a question mark over it, less than NB1. And then what you can show is that 1 minus eta over eta. So 1 minus eta, and this is equal to question mark 1 minus eta over eta. Actually, it's easier to think about this in terms of the gain. I'll write this in terms of the gain, where the gain is 1 over eta. So then you have okay, 1 over, yeah, gain minus 1 over gain less than or equal to gain minus 1. And that is always true because gain is bigger than 1. And so there you have it. So yeah, it's actually better to amplify before you lose rather than to amplify after the case. Better safe than sorry. Okay. That's a long-winded example exercise, but still it's useful. And people actually use this. This is actually a useful technique to prove there's some nice papers on quantum communication of bosonic channels where this kind of technique is used. So it's not just an academic exercise. It's a very, some very well-cited papers too. So this is not just an academic exercise, but it's actually a useful a relationship. Okay, next slide, Howie. Okay, that concludes me. No more of me talking. Now you get to listen to Dr. Howie Shi instead of Anthony Brady. I will be on standby. But that concludes the Gaussian channels, all that stuff. And now Howie's going to talk about single photon encodings, and then look at some of those Gaussian channels acting on single photons and wrap everything up. Okay. Yeah, take it away, Howie.
Okay. Okay, thanks for the introduction by Dr. Anthony Brady. We have learned how to describe the photonic dynamics using the unitaries and the quantum channels. So now we are ready to use the single photon to do some encodings for quantum information. The most widely used encoding method is the dual rail qubit. Photons can have many degrees of freedom, polarization, spatial, angular momentum, while each of those degrees of freedom can be described by a set of mode operators. Here, capital M is the number of the modes. We can generally focus on only 2 modes for the dual rail qubits. And we can define the logical states 0 and 1. They are both the single photon states. They are just photons at different modes. So we should distinguish 0 and 1 here from the Fox state 0 and 1, because the Fox state 0 is a vacuum here, while here 0 and 1 here, we mean the mode index, not the photon number.
Oh, by the way, Howie, if you want to point to something with your mouse, I just found something nice. If you go to annotate,
Ah,
there's a
okay.
pin, but there's a vanishing pin. So you'll click it and it'll just vanish by itself.
Let me try.
Yeah, so you can click draw, and then there's like a draw, one of the tools
Uh,
you do annotate through Zoom.
you said there's a vanishing pen.
Yeah. You know how you can do the pin through Zoom, through annotate?
Yeah, I
And
see
then,
draw here.
yeah, and there's one that
Draw.
says vanishing pin. If you click on the icon,
Let me see. Oh, I see.
yeah, and then if you just move off
Oh,
it, yeah, it vanishes.
that's cool.
And so people see, yeah, you can see that better than your mouse.
Okay,
Okay.
thanks.
I just
Yeah,
found that. Yeah.
cool thing. Yeah. Okay, so yeah, so here vacuum means the zero stay in the Fock state, the Fock basis. Mathematically, here the vacuum state is actually a tensor product of the two subspaces for the two modes, 1 and 2. And here the annihilation operators are defined for the first mode and the second mode, respectively. To give you some intuition, let's consider the single qubit operation, specifically the passive operations. The passive operation means that there's no photon addition or subtraction. The photon number must be conserved. And equivalently, you can write the commutation relation for the passive operations. They must commute with the total photon number so that the total photon number can be reserved. The passive operations basically consists of unitary beam splitters, UBS, and phase shifters, U phi. They have the Hamiltonians as derived here. So here's an exercise to show that. Let's show that for any Hamiltonian of this form, which is basically photon swapping between the mode I and J with some coefficient Hij. Commute with the total photon number operator, and as we have mentioned, it must conserve the photon number. So this problem is equivalent to show this commutation relation equal to 0. We can use the well-known equation here and the canonical commutation relationship here. And let me give you a quick derivation just for fun. Seems like my surface is not a co-host. So, oh, let me see. Okay, cool. So let's derive this equation. Now let's use the decomposition. this is the first step. And we can further decompose this into now I'm writing this part. Well, we should note that the same annihilation operators commutes A and A. So we will only have the A and A dagger term. This term will give us minus AJ. There's a minus sign because I'm using this equation for CA, which is minus AI. This term is canceled, so and now let's consider this term. Again, we only keep the dagger and the non-dagger term in the notation. So now we are ready to plug in the canonical commutation relation, which is minus IK for green term. Oh, actually here AK should be at the end because AK is in the end. So this is AI times AK. The commutation relation gives delta JK. Okay, so here we take the sum over the Kronecker symbol delta, which gives this basically means I should make the two subscripts equal. K should be equal to I. So the first term goes to, there's no sum here. The first term goes to K equal to I. And the second term goes to J, K equal to J, so K, J. Now we see they cancel each other. So the final result is 0. They cancel. Yeah, it's a long derivation, but we see that by trivial derivations, we can verify any Hamiltonian of such photon swapping form commutes with the total photon number. So it's photon number, total photon number conserving. Now let's proceed to the beam splitter transform, which is a specific type of the passive transformation. For example, if you have the zero state, the zero logic state input, which corresponds to one photon at mode 1 and zero photon at mode 2, you will have a superposition state at the output. So the photon input is splitted by the beam splitter. The beam splitting ratio is described by theta. The transmissivity is cosine squared theta. And here's the full unitary matrix. Oh, maybe you cannot. Okay. Okay. So here's the full unitary matrix to describe the beam splitter transformation VBS. This is derived from the Hamiltonian we have mentioned. It's easy to check that this matrix V is unitary. This matrix can be easily created in practice using the Mach-Zehnder interferometry. Yeah, and this matrix will fulfill such input-output relation if the input is eigenstate 0 or 1. Here's a poll. Can we implement the Pauli X matrix using the beam splitter? Consider two input modes into a general beam splitter. We have such unitary matrix transfer. Up to a global phase, can we implement the Pauli X matrix expressed by this? The answer is yes and no. Yeah, let me pull up the poll. Yeah, this is not so hard. If you can just look at the 1 term. You can simply let cosine theta equal to 0, and you can solve the values for theta. And then have 20 seconds left. Five seconds left. Let's give you 10 more seconds. Okay, time is up. Okay, the answer is A. Yeah, so most of you chose the right answer. Here, yeah, as I mentioned, you can easily solve theta by comparing the 1 term. So cosine theta equal to 0 gives you theta equal to pi over 2. And then you can solve phi. Yeah, so phi should be pi over 2 too. And then you get the Pauli X matrix. Here's an exercise. So let's consider the V5 VBS for phase shifts and the beam splitter. Can we combine them to further produce the Hadamard matrix? This is a very important matrix for quantum computing. This is actually a specific beam splitter. So we can implement this by choosing phi1 equal to 0, phi2 equal to pi. Then we can make the phase shifter V5 be a Z Pauli matrix. And then we can choose theta equal to pi over 4. Then we can make the beam splitter matrix to be in this form. You can see that this is almost equal to the Hadamard up to a phase shift. And the phase shift can be done by the V5 phase shifter. And in the end, you have the Hadamard matrix value. In practice, when choosing the photonic degree of freedom, we have a few practical factors to consider. Is the degree of freedom easy to manipulate in the practical engineering? Is the degree of freedom robust to the experimental noise, the loss and noise, and the thermal environment? And if necessary, can we scale up for quantum information processing with many photons? This compared to the Google quantum chips, they must use many physical qubits to encode only one logical qubit. The same thing applies to photonics chips too. We want many photons to suppress the error rate in the quantum computing. So there are also more factors to be included, while these three will be the first to consider. So the common encodings are spatial encoding, polarization encoding, and time-bin encoding. For spatial encoding, you have the same frequency and polarization for all modes, while you have different paths for different modes and for different encoded qubits. Their interaction can be fulfilled by overlapping the paths using, for example, the beam splitter. And second, the polarization encoding uses different polarization to encode the photon. The interaction can be fulfilled by birefringent materials. They can be fulfilled by nonlinear crystals, for example, the lithium niobate or KTP. And third, we can do the time-bin encoding using different time-bin intervals. This encoding requires fast optical switches and delays, so it's typically more costly. All those three encodings have their own pros and cons. For example, the spatial encoding can be very bulky, and the polarization encoding must use nonlinear crystals. So it could be also bulky and costly. And actually, the nonlinear coefficient is typically very low. And at last, the time-bin encoding, as I have mentioned, this could be very costly if you want fast optical switching. So in practice, we should choose a specific encoding according to your specific application scenario. And actually, we can swap between those encoding methods. For example, here we show how we can swap between polarization encoding and spatial encoding. Here, given two polarization modes, H and V, and the two spatial modes, 1 and 2, we can use a PBS, the polarizing beam splitter, to fulfill such encoding swapping. Here's a schematic for such swapping. This PBS basically transmits H while reflects V polarization. So here you can see the information marked by different colors. Encoded on H is transmitted directly, as shown on the magenta color and the brown color, while the information encoded on V is reflected. So at the output side, you can see that the information is encoded on the H and V instead of the, it's encoded on the spatial path instead of the H and V now. With this encoding methods in hand, now we should model the practical performance. We should include the practical loss and noise and consider how the single photon will evolve under such imperfections. We will consider the thermal loss channel for a teaser. This is a very important channel because all the communication links are over noisy fibers or free space, which can be modeled by this thermal loss channel. Anthony has given a brief introduction about it. So it basically, we consider a attenuation eta on the input field while there's a thermal source, E, with some thermal photon number NE mixed in the output. This attenuation coefficient eta typically decays. Well, it's actually the transmissivity. Sorry, it's not the attenuation. The transmissivity will decay with the fiber length L. This is the Beer-Lambertian law for the absorption media, like fibers. As Anthony has mentioned, we can further decompose this thermal loss channel into two pure loss channel and the pure amplified channel, AG and L tau. So we want to have tau multiplied by G equal to the final overall transmissivity eta, and the thermal photon number produced by this concatenation equal to the overall the thermal photon number NE. Then we have these two equations here. Maybe I should make my cursor always the spotlight. Yeah, okay. Okay, so solving these two equations, we can get the parameters we needed, tau and G, dependent on eta and NE. So the decomposition, as Anthony has shown, we can describe such decomposition with very neat diagrams. we know that the amplifier yeah, the amplifier can be drawing this and the loss. Okay, simply draw as this. So overall, we can see a thermal loss channel can be decomposed by these two quantum limited pure loss channel and pure amplified channel, where the tau and G has been solved here. We can see that G increases if the thermal photon number NE increases, and tau is proportional to the transmissivity eta, as we expected.
And just to recall, I'll go back to the slide. And just to recall everyone that we went over this a bit before too, that if you concatenate a loss channel with an amplifier channel, it could be many different channels, but for example, but it depends on conditions of what tau G is. In this case, tau G is less than 1, and so this is a thermal loss channel. So yeah, that's all.
Yeah, indeed, we can also generalize such decomposition to amplified channels if eta larger than 1, but that's another story. Yeah, the method will be very similar. Okay, so now we can, why did we do such decomposition? Because we know that the pure loss and the pure amplifier has very simple operator sum representation. And by such decomposition, we can further use this simple operator sum representation to describe thermal loss. Here we show the known results for the known results of the operator sum representation of pure loss and the pure amplifier. A and B are their cross operators. And then their concatenation thermal loss can be simply expressed as yeah, this is the concatenation of those two channels. Yeah, you can regard it as rho first operated by cross operator A, and then operated by the cross operator B's. First loss and then amplifiers. Here we give some intuition using a very simple input, the single photon state input, and which is actually the only state we are of interest in the dual rail single photon qubit encoding case. We have mentioned this in a poll that when you have a single photon input, you only have two cross operators left, A naught and A1, because all the L larger than 1 terms will be lost. And goes to zero, diminish. This result tells us with probability tau, the photon is transmitted. This is the event where A naught happens. A naught is basically an identity, gives you tau rho one, where rho one is the input. With the complementary probability 1 minus tau, you will have the photon lost. The input will be converted, will be operated by the loss event A1. The output is a vacuum state. Okay, here's the fourth pole. When acting on the single photon state, the pure loss channel is equivalent to an erasure channel, with the erasure probability epsilon equal to 1 minus 1 minus tau. So now what is the erasure state in this case? Know that we are, thank you. Know that we are losing photon via the loss. What does the photon loss mean? Meaning that the single photon decays into the vacuum state. Yeah, the answer is obvious.
We'll give about 20 more seconds, guys. Okay. Yeah, there you go.
Yeah. So answer is A, the vacuum state. When the photon is lost, it's converted into a vacuum state. Here we continue to analyze the single photon input case for the thermal loss channel. If you have we have wrapped up the first part for loss, the pure loss channel. We should know that there's an amplifier channel as the second part, and this part will be more complicated because we will add photons. It's not a passive operation. So well, actually, I think B0 and B1 might not be sufficient. Well, let's consider first the B0 and B1. Those cross operators. We append them to the first pure loss channels. This will result in 4 different possibilities. 2 times 2 equals to 4. So the first case is if in both channels we have the index L equal to 0 event, which means that there's nothing happen. Then this means the photon is unaffected, and here we solve the probability here as tau over g squared. The second event corresponds to nothing happened for the first channel, while the second channel adds a photon to our output. This will give us one noisy photon added to the state at the output, while you have no information about the input. The probability is here so as to, I think I will give an explanation later. No. Well,
Yeah,
yeah.
eventually it will. It'll give something. Yeah.
Yeah. Yeah. Well, here we just show the result. We solve the amplitude here. And the third event is the loss event happens for the first channel, while for the second amplified channel, there's nothing happen. Then we solve the probability here. This corresponds to the event that the input photon just gets lost. We have vacuum as the output. The fourth event corresponds to both loss and photon adding happens for both channels. In this case, the input photon is lost while, for the second case, the photon is added to state. So the input is still there. We have a two photon output. And for the fourth event, we have nothing, we have no information about the input. The input photon is lost. And it's replaced with the single noisy photon comes from the environment, from the amplifier.
Yeah. So
The output is low one.
some small bit of explanation is that anytime that there's a photon added to the state, um, the expression goes like G minus one, because G equals one is basically there's no amplification whatsoever, nothing happens. And so the amplifier is what adds photons to the state from the environment. And so anything that goes like G minus one, that's where that comes from. And at the end of the day, what will come up is that this G minus one will be basically proportional to the number of environmental thermal photons, this NE number that we introduced before. And so, yeah.
Yeah, and this can, what Anthony have said can actually be verified in those probability amplitudes. If the photon is transmitted in the first channel loss, you can see if A is A naught, then you will have this tau coefficient, while the G minus one coefficient comes from whenever the photon adding happens in the amplifier, B1. If B1 happens, you have this G minus one factor. Yeah. So continue with the calculation. We have the final overall density matrix. It has three parts. The first term contains two cases. The successful transmission where nothing happens, and if the input is lost while the amplifier adds a photon in it. Both gives one photon output. And while the vacuum and the two photon state corresponds to the only loss present case and the only photon adding event happens case. We can describe those events into by this successful transmission event and random photon. Random photon is for the case where the input photon is lost while the amplifier adds a photon. We call it a random photon event. And receive nothing cases only loss happens and no photon is added. Receive larger or equal to 2 photons corresponds to the well, yeah, all the other possibilities. Well, yeah, so this is exercise to allow us to calculate to approximate the output statistics at the limit, the asymptotic limit of low thermal noise, meaning an E of the environment, the photon number of the environment goes to 0. In this case, we can do a Taylor expansion over the probabilities we have derived. Now let's show that the photon number larger or equal to 2 case has a probability in this form. And let's try to intuitively explain this out. Yeah, so here's the result in the previous slides. And after Taylor expansion, we have those results up to the first order about NE. We can intuitively understand those probabilities by considering we can consider the first channel, the pure loss channel, yields 2 events, okay, of probability eta or 1 minus eta. Eta gives eta corresponds to an event where you have the photon transmitted. And the other probability, 1 minus eta, corresponds to I see a question. I will answer this later. And the other event is the input photon lost, corresponds to the probability 1 minus eta. And the second channel has also gives you a similar Bernoulli event with probability 1 minus eta NE to have a thermal photon goes in. Because you have NE thermal photons in the environment, while the the mixed in probability is 1 minus eta. Okay, so multiply together the thermal photon mixed in, the probability of at least one thermal photon mixed in is NE times 1 minus eta. So by such intuitive understanding, we can interpret the first event success corresponds to first you have the photon transmitted with probability eta, and then you have the thermal photon not mixed in. So it should be 1 minus eta times NE. Well, here the coefficient 3 comes from the Taylor expansion. Here's about the third order polynomial. And similarly for a random photon event, this probability can be interpreted As first you have for the loss channel, you must have the photon lost. The probability is 1 minus eta. Then you have in the second amplified channel, you have a thermal photon mixed in. The probability is 1 minus eta times NE. Overall is 1 minus eta squared times NE. And the third event, the vacuum state event, requires us to have first the photon is lost in the loss channel. You have 1 minus eta probability. Then you must have no thermal photon mixed in. So the probability is 1 minus the mixed in probability, 1 minus eta NE. Here, this 2 comes from the Taylor expansion. You have 1. This is actually related to more complicated numerics. You have 1 minus 2, 1 minus eta, and you have another term about NE here in the numerator. They cancel each other to give this term. Yeah, this requires more calculation. Well, and in the end, you have the otherwise probability equal to 1 minus the sum of all the 3 events above. This result is 2 times eta times 1 minus eta NE. This can also be interpreted by our intuitive decomposition. The first you must have the input photon transmitted. So you have the first factor eta. And then you must have a thermal photon added in. The probability is 1 minus eta times NE. Okay, so overall you have this for the event that has 2 or more photons. Okay, so finally we have finished this course. Let's give a recap. What have been covered in this course? We have discussed how photons are good for everything, sensing, computing, communication. But I think we have been focusing on communication described by the channels. Well, the fiber loss can be described by the thermal loss channel, as Anthony mentioned. And we have reviewed general descriptions of evolution and quantum channels. The quantum channel can be represented by cross operators. And yeah, I think we skipped the part about purification, the unitary extension, but they are important tools if you want to do theories, to derive some quantum capacities, to derive some ultimate precision limits of sensing. You might want those tools, purification and unitary extensions. And we also analyzed the Gaussian bosonic channels, including loss amplifiers and additive Gaussian noise, AGN, and their influence at the single photon level. We also surveyed the single photon encodings and the single qubit operations. For example, the passive operations on the dual rail qubit, where we consider only single photon input, which is enough for the dual rail case. And we consider the energy conserving operations, the beam speeders and the phase shifters. So yeah, that's
Great.
Great.
Yeah, I think that's about it. I don't know if Brianna's there. Brianna, you there? She's taking a nap. Rightfully so. I guess that's about it. I think there's maybe some course evaluation that probably will be sent around, but that's it from us. Hopefully, if you want, any lecture notes were sent out. Not sure if the slides were shared, but we can possibly talk to Brianna about sharing the slides as well. Thank you guys. We're gonna go probably eat, take naps. Have a nice day. See you,
Have a
Howard.
nice day.
Okay. Can I end this thing?